The following presentation of how core cognition might implement quantum cognition is a slightly extended version of the presentation given on April 26, 2016 at the Science of Consciousness Conference in Tucson. This presentation will consist of brief overviews of core cognition and quantum cognition research, a consideration of the formal requirements for a quantum theory of cognition, followed by a discussion of what minimal quantum-like modeling might entail, and ending with a conclusion and implications. The core cognition systems, or innate representational resources, that I will be discussing have emerged from research in numerative cognition. Three core processes are presently recognized: set-based quantification, parallel individuation, also known as the object tracking system, and the analog magnitude, or equivalently, the approximate number system. I will also advocate for a fourth core process, mental rotation. Set-based quantification emerges in a variety of research contexts. I will follow the thread by which it is initially identified by Vender and Rothkegel in 2000 as a sub-process of subitizing by which the pattern is separated from the background as a whole. In 2008, Halberta and Fagenson argue for a third distinct core process, the ability to bind representations into sets. Set-based quantification is distinct from the system of the OTS, the ANS, and is prior to language. This departs from Carey's linguistic set-based quantification, but in fact may underlie it. Set-based quantification is involved in the representation of objects, sets, and ensembles by chunking, as is currently discussed by Fagenson. Parallel individuation, or the object tracking system, grew out of research on subitizing and working memory. It is characterized by its limited capacity. Infants can discriminate set sizes from 1 to 3 and adults set sizes from 1 to 4, yet those discriminations are precise and equal. It is primarily visuospatial, but it also plays a role in auditory and tactile discrimination. It should be emphasized it is not a number system. Its representations are simply discrete tokens. Evidence for the OTS is obtained from several areas of research. Developmentally, it's observed with newborns, and it displays nearly adult levels by 1 year of age. It is generally observed across human cultures and across species as well, observed in whales, primates, and birds. Neurally, it's associated with the right temporal parietal junction associated with visual attention. The third core system is the analog magnitude, or approximate number system. It is sometimes referred to as the number sense. Unlike the OTS, it is unlimited by set size. However, it is noisy, displaying approximate magnitude representations that follow Weber's law. It has two characteristic effects: the distance effect, where a number such as 5 versus 10 is easier to discriminate than 5 versus 6, and the size effect, where 5 versus 6 is easier to discriminate than 10 versus 11. It has amodal or multimodal representations, including spatial, oral, tactile, and the like. It supports ordinal relations and magnitude comparisons of more versus less, and it supports approximate addition and subtraction. Developmental evidence for the ANS shows that acuity improves from infancy through adolescence to adulthood. Comparatively, it is observed across human cultures. However, ANS acuity is dependent on culture and education. Also, it is attributed to a wide variety of species. Neurally, it's associated with the horizontal part of the intraparietal sulcus. This list displays the range of species displaying the ANS signature. Associated with the ANS are the phenomena of the SNARK effect. SNARK is an acronym for Spatio-Numerical Association of Response Codes. It was discovered by De N, who informally associated the SNARK effect with the notion of a mental number line. Evidence for the snark effect is grounded in the close association of numerical magnitude with both spatial extent and temporal duration. Developmentally, it is observed in infants, older children, and adults. Neural evidence points to the involvement of the interparietal sulcus and the prefrontal cortex. Comparative studies provide evidence of snark behaviors from both human and macaque. An alternative approach to interpreting snark phenomena is atom, a theory of magnitude that was formulated by Walsh and further developed by Lourenco. This theory emphasizes the role of non-numerical magnitudes as well as numerical magnitudes. The supporting evidence for this includes cross-magnitude interactions, correlations in precision of numerical and non-numerical representations, and training and transfer across magnitudes. In general terms, the SNARK approach can be seen as concerned with integration of initially separate systems, whereas the GMS is concerned with progressive differentiation of a single generalized system. The aspects shared by both systems that I wish to highlight are that numerical and non-numerical magnitude systems share an abstract, more or less order relation, and that both systems provide evidence for an analog directed magnitude representation, something akin to what we would ordinarily consider as a vector. I would like to consider the possibility of a fourth core system, namely mental rotation. Shepard and Metzler initiated the study of mental rotation in 1971. In their classic study, they asked participants to mentally rotate an image of a configuration of blocks until that configuration was aligned with a second configuration that was either identical or an optical isomer. What they found was that there was a linear relationship between the angle of rotation and the time taken to carry out the rotation, just as there would be in the case of physical rotation. By 1982, Shepard and co-workers presented a general and robust case for mental rotation based on a variety of experimental designs. Mental rotation has been found to have the following characteristics. Reaction time is a linear function of rotation angle. Mental rotation involves both rotation in plane and rotation in depth, and reaction times are not greater for rotation in depth than they are for rotation in plane. Mental rotation is not limited to visual image rotation. There is some evidence for haptic rotation. In general, after several decades of extensive research, it is generally agreed that mental rotation is an incremental analog transformation process. Evidence for mental rotation has been found using a variety of research methods. Mental rotation has progressed from being an object of behavioral studies to being a behavioral metric for testing differences in age, gender, and ability. Developmental studies have found that mental rotation tracking ability improves with age. Also, gender-based disparities have been observed. Comparative studies have shown that mental rotation is more developed in humans than great apes. A motor variant of mental rotation has been studied in monkeys. The neural evidence for mental rotation has been obtained using fMRI, EEG, MEG, PET, and other observing systems. It has been found that mental rotation involves the intraparietal sulcus, and in particular the dorsal object-sensitive region and the ventral caudal region that contribute to the spatial configuration of object features and to the spatial coordinate transformations used both for mental rotation and object recognition tasks. These specifically involve object model verification by matching between object working memory representations. As well, the superior parietal lobule is involved with the mental imagery of object rotation. Recently, it's been suggested that mental rotation and basic numerical skills may derive from shared spatial representational mechanisms. Having reviewed core cognition research, in particular the 4 core systems with numerical content, I would like to engage my second topic, quantum cognition. Quantum cognition is a new and rapidly developing area of research with many outstanding questions, such as those stated in this recent review of the topic by Bruza, Wang, and Busemeyer. Specifically, I would like to focus the remainder of my presentation on the third bulleted question. If the quantum cognition research program does not rely on the assumption that the brain is some type of quantum computer, how then does the brain accomplish quantum-like behavior? I would first like to clarify what quantum cognition is and what it is not. Quantum cognition is the application of a probability theory and its associated logic that was first developed for physical microprocesses to the description of cognitive and psychological processes. Quantum cognition is not an attempt to theoretically link cognitive processes in any direct fashion to the quantum mechanical behaviors of subcellular or macromolecular systems. This begs the question, why is quantum cognition necessary or even relevant? Quantum cognition has been introduced to provide a unifying and simplifying framework for the description of a growing number of cognitive phenomena that resist explanation based on the classical probability theory and Boolean logic that are typically utilized in cognitive science. These phenomena display order and interference effects that are characteristic of non-commutative and superposed states in quantum phenomena, whose description requires a different quantum probability theory and a non-Boolean logic. Quantum cognition research has developed to the extent that it is now finding application in a wide variety of areas, including the following. But what exactly would a quantum theory of cognition entail? Quantum physics texts often contain a formal list of postulates of quantum mechanics, stipulating states represented by linear operators in complex Hilbert space, projection operators, tensor products, and so forth. How much of the formalism of quantum mechanics is actually needed to carry out quantum-like modeling in cognitive science? Wang and Busemeyer have stated simplified postulates that are relevant to quantum-like modeling. Postulate 1, a person's belief about an object in question is represented by a state vector in multidimensional feature space, technically an n-dimensional Hilbert space. Postulate 2, a potential response to a question is represented by a subspace of the multidimensional feature space. Postulate 3, the probability of responding to an opinion question equals the squared length of the projection of the state vector onto the response subspace. Postulate 4, the updated belief state after deciding an answer to a question equals the normalized projection on the subspace representing the answer. The three graphs below illustrate the application of these postulates to three well-known case studies that exhibit order effects. Each graph illustrates the effects of projection of a state vector, labeled S, onto two different axes or subspaces. The general point to be taken here is that in each case, a cognitive state is represented by a directed magnitude or vector, which is projected onto subspaces that lie at different angles with respect to the state vector. The question arises whether the core systems of cognition, particularly the analog magnitude system and mental rotation, could implement quantum-like modeling. Specifically, could the mental image of a directed magnitude or vector be subject to mental rotation? There is some evidence that this might in fact be the case, evidence that, curiously enough, comes from a case study of the historical development of complex numbers. From first chance encounter to final christening, the conceptualization of complex numbers took almost 2 millennia to complete. At first unacknowledged, then declared impossible, false, and imaginary complex numbers ultimately became accepted by the general community of mathematicians when they could finally be visualized. What the square root of a negative quantity might be was a long-standing mystery. When real numbers are associated with points on a number line, imaginary numbers are nowhere to be found. Only when analytic geometry had matured to a point where a two-dimensional coordinate system had evolved and numbers, both positive and negative, could be represented as directed magnitudes or vectors, did it become possible to visualize the square root of -1, or I, as a rotation. I will claim that the discovery of the geometrical significance of complex numbers was the result of the mental rotation of an image of a directed magnitude representing a real number. As a final footnote, it is worth pointing out that complex numbers are a necessary attribute of the formalism of quantum theory, accounting for the order and interference effects that quantum systems display. To conclude, it seems reasonable to explore further the possibility that core systems might support simple modeling of quantum cognitive phenomena, but the evidence at present comprises only a few dots on the projection screen, and these dots need to be confirmed and connected. Among the very many issues to be sorted out is how the cognitive operations associated with normalizing and projecting cognitive state vectors can be better understood. Also, wider issues such as the percept-concept distinction need to be explored. Thank you for your interest in my presentation. Please send any comments or questions that you may have to the following email address. Thank you.